So hello everyone, this is Cfrg. I hope everyone can see the slides and can hear me. This is Cfrg, and we'll start with research group status. Alexei Melnikov, Nick Sullivan, and Stanislav Smishlev as chairs. This session has been recorded automatically. We have a minute taker. Thank you very much to Alexei. We have a Jabber relay, thanks to Jonathan Holland. We have our blue sheets automatically generated, and you have a link to the minutes when they will be ready. So you can see the note well. I hope you saw it sometime. Cfrg is a research group of IETF. You can look at RFC 7418 to know a little more about IETF. The slides are available using this link, and all documents are available in Data Tracker. So we have quite a busy agenda. We'll start with a Cfrg update. Then we have a talk on Kangaroo 12, on two PEGs that were selected after the PEG selection process. One status update about, sorry? One status update about VOPRF, about RSA blind signatures, about Frost, about key committing AED, and about some possible modification of VOPRF that can be needed for privacy pass. And in other business in the end. Maybe any agenda bash?
Yeah, I just want to point out the slides are not advancing on our perspective. That's what Watson was trying to say.
Yes.
Now we see the agenda. But,
can you see the agenda now?
Yes.
Okay, so we'll proceed. Not in full screen, sorry. So I can replay the slides with some admin trivia. I hope you saw not well. I hope you know the goals of the IRPF, and there are links to the session slides and to the data tracker. So we have quite a busy agenda. I won't repeat it one more time, I hope. So let's go to the document status. In fact, we have a lot of new work done from November, but we don't have any new RFCs. We have one update of Argon 2. Only yesterday there was a new version, so we hope that Argon 2 will be published before the next meeting, because it has undergone IETF conflict review, and there was only a small comment, so I hope that every concern is addressed now. We have HPK document after research group last call and after document Shepherd review. It's in the IETF chair review queue. And we have plenty of active Cfrg drafts. So about spec 2 draft. It has been updated, and research group last call has finished successfully. Now we are waiting for Shepherd's review. It's mine review. We have some questions to be addressed, so I hope that we'll proceed in a couple of weeks. We don't have any changes with Hefty curve draft. We have updated VRF draft. Now it's in the research group last call status. The Kangaroo 12 draft has been updated, and we'll have a presentation about Kangaroo 12 today. The OpenRF has been updated too. No other news with it. No news about BLS draft. A major update of parent-friendly curves, and now we are waiting for a second rescheduled last call. We have an updated version of AD limits draft and about both spec drafts, OPEC and CPACE. We'll have presentations about both of them today. The first draft has been adopted, and we'll have a presentation in the agenda today. So the crypto review panel is still working, is still providing good reviews, and still happy to do new reviews for the Cfrg or for any other requests from ISE or IETF groups. So let's move to slides, and since some people wanted the slides to be shared to the full screen, and there seems to be some technical issues on my side, can I ask Nick to project slides from his side?
Just a second, Colin's in the queue. Let's take a question from him.
Hi, just for on the draft status, if you can hear me.
Yes.
Yes. Okay. So for HPKE, my apologies. I know this has been waiting for me for a while. I have not forgotten that the pandemic is rather getting in the way, but I hope to get to it shortly. For the Argon, is it Argon 12? I'm forgetting the acronym. If the chairs can just confirm that the changes are satisfactory, then I'll get that moving quickly.
Okay, yeah, I'll check. I just saw the updated version this week, but I didn't get around to it yet. So.
Yeah. Okay. Thank you.
Argon 2 was updated only yesterday, so we hope to see it in a couple of days. And about the HPKE, Colin, thanks a lot for a lot of comments from your side, because I think that a lot of improvements of HPKE was done after your first review. So I hope that no more big issues with HPKE will occur before the next stage. Nick, could you please share the slides? Now we only say that screen share has been, oh, yes, we see it. So please, Jill, Kangaroo 12, please start.
Hello, can you hear me?
Yes, we can hear you. Please start.
Okay, thank you. So yes, my name is Gilles Vanache. I work for ST Microelectronics in Belgium, and I'm one of the editors of the draft on Kangaroo 12. So I would like to thank you for this opportunity, and I would like to make a brief status of the draft. Can you go to the next slide, please? Thank you. So as a starter, here is a quick refresh about Kangaroo 12. So it's a hash function, or more precisely a ZOF, an extendable output function, because it has a variable output size, and it's based on the NIST standard Shake 128. So the differences between Shake 128 and Kangaroo 12 are, the two main differences are, first, we reduce the number of rounds from 24 to 12 rounds. And the second change is that we added a mode of operation that exploit parallelism, and in particular SIMD instruction sets. So the result is a ZOF that is at the same time secure and fast, of course. So it's not my purpose to discuss again why it's secure and fast, because I think Benoit did that fine a few times already. So that's not the goal. I'm just going to give you a couple of hints. So about security, the key point is that Kangaroo 12 reuses the cryptanalysis of the reduced round Ketchak or SHA-3. So the round function is exactly the same, which means that we can rely on more than 10 years of cryptanalysis by the community. So for instance, as of today, the best collision preimage and second preimage attacks against SHAKE-128 work only up to 5 rounds, and so the same goes for Kangaroo 12. So about the speed, it's faster than MD5, SHA-1 or SHA-2, especially when the processor has IMD instruction sets. And for instance, if you take the Skylake X or Cascade Lake architectures, then Kangaroo 12 tops at about half a cycle per byte, which is roughly 7 times faster than SHA-1 on that platform. And well, in general, it's faster than SHA-2 and SHA-3. Can you go to the next slide, please? Thank you. So here is a log of the draft. So it became a working group item in August 2019. Sorry. Then we fixed some typos. We had the chance of getting some reviews from the crypto review panel from Jean-Philippe Masson and Thomas Pornin, and we integrated these their comments in versions 02 and 03 together with the comments from Stephen Farrell. We also received some requests for clarification from Pascal Junot, and these were integrated in version 04. Then Nick sent a last call in October last year. There was one mail of positive feedback from Christoph Dobrownik, and then a reminder. Yes, version 05 is just because Benoit needed to change his email address. And finally, we got some comments from Mark Pendame Rogers, which I think we addressed. I mean, at least we proposed something that would address, which is simply one sentence to be added at the end of the document. But he didn't confirm if that was okay for him or not yet. So that's the status, I would say. So globally, we've received positive feedback, but not that much feedback, especially after the last call. So we thought that at this point, it would be a good idea maybe to stress again our motivation for suggesting Kangaroo 12. And that's the purpose of this presentation, basically. Can you go to the next slide, please? Thank you. So the question is, why do we think that Kangaroo 12 is actually interesting for the internet community? And I see two sets of arguments. The first main arguments are about the implementation properties. So we think that these implementation properties are quite unique among hash functions or symmetric crypto primitives in general. So specifically, our run function uses only bitwise degree 2 operations like XORs and ANDs and rotations. And this means that when it's implemented in the hardware, the critical path is really short. So this explains why Keccak is fast in hardware as well as energy efficient. But even if you're not interested in hardware implementation per se, of course, a CPU is a piece of hardware, so this may have an impact in the long run. To illustrate that, if you take the AVX512 instruction set, there is a new instruction that can perform any bitwise operation on 3 operands, so that you can just specify the truth table of this operation. And this is an example of an instruction that I think is possible thanks to the short critical path of such operations. Another important implementation aspect is when one has to protect against special kinds of side channel attacks like differential power analysis, DPA. And we know that these protections are quite expensive, but the degree 2 operations make these protections less expensive than on ARX designs or even the AES. So in the end, I think Kangaroo 12 has nice implementation properties that other primitives usually don't have. And at least this brings some good diversity in the portfolio of symmetric primitives. The second set of arguments is more, I would say, economical. It's about reuse of things that were already done. So first is cryptanalysis. So cryptanalysis takes significant time and effort, and Kangaroo 12 can leverage on these investments. We can reuse all the cryptanalysis done on Keccak since 2008. Another point is the reuse of implementations. So obviously we can reuse code from SHA-3 and adapt it to Kangaroo 12 quite easily. But I also have in mind a recent trend that some vendors are adding hardware assistance for different standard hash functions. And for instance, ARM has defined some SHA-3 instructions in their 64-bit processor optional instructions. So Kangaroo 12 can benefit from these instructions. And as a matter of fact, these instructions are present in the latest Apple A14 and M1 processors. And concretely, if you're interested in some figures based on benchmarks from Andy Polyakov, I expect that Kangaroo 12 can run at less than 1 cycle per byte on the M1. And to compare apples to apples, if you consider the hardware accelerated SHA-512 on the same platform, it would be twice, at least twice faster. So yeah, just to sum up, I think that these points are, at least they convince me that Kangaroo 12 is something interesting and valuable for the community. And actually, that's all I wanted to say. So thank you very much for your attention.
Thanks a lot, Jim. Any questions? Going once, going twice. Okay, then. Thanks a lot.
Thank you.
Please, Bjorn Hassel, raise a presentation about the current status of CPACE draft. It's the balanced pack that was the winner of pack selection contest last year. So we have the CPACE draft updated recently. So Bjorn, please tell us about the current status.
So hello, you hear me?
Yeah.
Yes.
Okay, so I'll take your slide there. So I'd like to give you an update on the current progresses regarding the CPACE draft. Up. Do you see my screen now, or up?
No, I'm afraid we don't.
Okay, wait a moment. Should be there now.
Yes.
Okay. So to give you an update, basically the news is that we have now completed the security analysis for CPACE in different variants, and we have published it in a paper which is online, which also has seen review, so that we are convinced and have sound results that also the new results in the paper are sound. So the results in a nutshell are that the different CPACE protocol variants that we consider in the current draft provide strong security guarantees. We have composability and adaptive security under relaxed assumptions, which is the strong simultaneous Diffie-Hellman assumption, which is less than we had previously. It's a decisional Diffie-Hellman type assumption. The main part is that we closely looked at the properties that we need for the map-to-point primitive. Previously, the maps have been considered as a random oracle, and in our analysis, we were able to remove this requirement and extract the actual need that we and the requirements that we have to impose on the mapping primitive. So good news is that all the security relevant properties that we actually need are fulfilled by the maps, which are defined by the #2curve draft. And potentially, we believe that our strategy might also be useful for analyzing the constructions in the OPRF draft. Basically, one important result of our analysis is that we don't actually need non-uniform maps for security. CPACE is also secure in the structure construction, and the cofactor does not impact security. For the next step, we have sketched our plan for the RFC and the strategy in Appendix F of the paper. And our objective has been to take the perspective of a user of CPACE, which will probably try to minimize the need of adaptations in his existing ecosystem when trying to integrate CPACE there. We have identified 3 subsystems and chosen 3 tailored variants, which the first one is considering implementation on single coordinate letters, such as X25519. The second ecosystem would be implementation that use group abstractions such as Ristretto. And the third ecosystem would be implementations that use conventional short wire stress approaches, for instance, NIST P256. So for X25519, we would be using a non-uniform alligator 2 without cofactor clearing. And as a result, a CPACE implementation will only need alligator 2 in addition to X25519 or X448. And we have analyzed whether the present sampling process for secret Scala that is used for these primitives, which is also known as Scala clamping, is secure also for CPACE, and that's the case. So and there's also no need for an explicit additional point verification code, since X25519 and X448 have twist security, and given that, we just need to check for the neutral elements. So existing X25519 and X448 is suitable for CPACE as is. Similarly, for Ristretto and DCAF, we would be using the built-in uniform map tries and add construction that comes with the abstraction. And also there, slightly non-uniform sampling of secret scalas that is commonly used there is also no problem for CPACE. And point verification is enforced by the encode and decode primitives. So this will make CPACE implementations most straightforward for Ristretto. We found a sample implementation online, which we plan to use for deriving test vectors. For short wire stress, we would be using the non-uniform encode to curve construction from the hash to curve draft. And of course, in this subsystem, conventional point verification is mandatory. And also, some care has to be taken when reusing existing libraries which target ECDH only at the moment, because for CPACE, one should really make sure that the secret scalas are sampled uniformly. So, for instance, rejection sampling. For the session keys, we will be using the X coordinate only, so to give more flexibility to implementers to choose also single coordinate ladder multiplication strategies, which exist also for short wire stress. Regarding implementations, there is not much new from our side, but we found several implementation prototypes in Go and Rust online, which we are looking at the moment. And our main topic is, at the moment, we are working on a reference implementation based on in ANSI for the short wire stress implementation. So, but in addition to the work that we are doing as an editor team, we are actively looking for partners which would be interested in preparing a CPACE integration into different crypto libraries. We believe that it might, for instance, be an interesting student project, instructive student project, and we would be welcome and happy if somebody would be raising his hand and saying, okay, we think that might be an interesting topic and we'd like to join. We are contacting different teams and universities, but if anybody is interested, it would be welcome if you get into touch with us. So we think that having others implemented would be a good real-world test for readability and completeness of the draft, and of course improve interoperability tests. Regarding the test vectors, there's not much news. We have in the last draft we have incorporated feedback, because it turned out that out in the wild there are different X25519 variants which require or don't require fully reduced field elements for the public points. And we have incorporated that in the draft. So summing up, we think that the main use is the security analysis. It might be interesting for the OPRF team to have a look at the proof strategy that we chose for CPACE, because in my perception, dealing with the map is one of the more difficult aspects, which is also a problem or a topic for the OPRF constructions that use Diffie-Hellman on elliptic curves. So we think that our approach might also provide a blueprint for avoiding that the map is modeled as a random oracle for the OPRF constructions. And we believe that it will most probably also allow for a more efficient single coordinate ladder when using a non-uniform map there. So secondly, regarding the hash-to-curve draft, we have reviewed it, and we think it's very well written and very clear. In our perception, it would be nice to have the exact requirements that we need for security for CPACE integrated it. So basically the invertibility property, which is already there in a subsection, but might be a bit more prominent. And on our wish list, it's not a must, but on our wish list would be to have a non-uniform encode-to-curve primitive and hash-to-curve draft. And this one without clearing the cofactor, because we believe that clearing the cofactor would anyway be something which any application level or protocol level would have to deal with, which is on top, one layer higher than the hash-to-curve layer. So we think that it might not be the best place to have cofactor consideration on the hash-to-curve level, but rather on the application level or the protocol level, which is using the results of hash-to-curve. Okay, and finally, I'd like to invite, I think it's a good idea to join forces for reference implementation with the OPRF and hash-to-curve team. I've already been in touch with Christopher Wood, but I'd like to ask anybody to give us a short note when we are working on reference implementations using maps, and we would be informing you and would be happy if you keep us synchronized of your advances there. Thank you very much.
Thanks a lot, Bjorn. Can I have the first question, if possible? There is great news that you have such a great improvement with security proof. But my question was about the implementations. If you can remember, during the pack selection process, there were some questions about identities that must be exchanged and arranged before the actual protocol. Do you feel that you occur some problems with implementing a CPACE with integration with some protocols, or there are no problems and all identities can be established before the protocol itself?
So indeed, the present protocol specification in the draft integrates the identities as part of the channel identifier into the protocol. We have discussed that also in the editor team, and we see currently two ways to deal with that. So in applications where we have the identities established beforehand, there's one, the straightforward way is to integrate it into the channel identifier field in the beginning. And in applications where it's only established as part of the protocol, one could not easily integrate it in the beginning, but and one will lose at this point the fact that the identities are authenticated as well. But one could use the identities and insert the identities in a final key confirmation round, as it is done, for instance, by TLS. And so in our opinion, it's not a real problem, as it will become part of the authenticated as part of the hash of the transcript in the higher level construction. So and that's So that's the present state of this discussion, and there also has been some feedback on the list. And in the current draft, we have in the current version of the draft, the identities are marked as recommended but not strictly mandatory. And as a part of the proof, of course, everything which is not integrated as a part of the channel identifier will not be authenticated.
Thanks a lot. Any other questions? Yes, Armando, please.
Hi. So, did you mention that it would be desirable to have a non-click cofactor in the hash-to-curve draft? So, in which cases this is an issue?
This provides the advantage is that when you clear the cofactor, if you use a map, for instance, such as alligator, you will receive the result of the mapping operation in affine coordinates. And if you start with removing the cofactor, you basically multiply by the cofactor, you will receive the result in projected coordinates. And you will have an additional inversion operation which you need in order to get it back to affine coordinates, so that you could use the most efficient scalar multiplication algorithm which works on affine coordinates. And that's the efficiency loss that you have an additional inversion which is not necessary security-wise, and it adds on implementation complexity a bit.
I think keeping all in projected coordinates can work, and also the scalar multiplication. I mean, the cofactor multiplication is just multiplied by ×4 or ×8. So I don't think it's a big issue, but we can analyze this later. Thank you.
Thank you, Armando. Please, Watson.
With alligator specific, well, okay, we don't need to get into the Cfrg thing. I do worry, what happens when someone comes along and defines another elliptic curve? How much work is there? Do you need to go write a CPake for this new curve, or is it generic enough that if it fits into one of the categories for the hash to curve draft, things will just work and people will know what to do? And it's really only the examples where these three integrations matter and the test vectors.
So basically, the news is all of the different constructions are secure and there's no risk security-wise. It's just ease of implementation. For instance, if you use the map, if you're using Ristretto, you probably won't be using the map which is currently defined in the hash to curve draft, because they are having a different construction and different built-in primitive, which does not match the implementation which is in the hash to curve draft. So, and security-wise, we don't have a problem. It's just ease of implementation if you consider the different existing code.
Thank you. Any other questions? I think no. Then thanks a lot, Bjorn. Please, let's proceed to the OPEC. So OPEC was the winner of pack selection process for augmented packs. So please, Chris, are you ready?
Can someone throw up the slides for me?
Nick, could you please share them, because I had some issues with full screen. I can try that again, but thanks, Nick.
So please. Oh, sorry, it's not the OPEC slides. Yes. So please start.
All right, thanks. Yeah, so this is just an update on opaque. Next slide, please. Stanislav already kind of gave it away, but opaque, for those who are unfamiliar, is basically it's an asymmetric password authenticated key exchange protocol that takes a number of cryptographic primitives, glues them together, and builds something quite nice. Next slide, please. The protocol basically runs in two phases. There's an offline registration phase wherein clients use their password to register public key credentials with the server. That are then stored in the server and then used later on in an online phase for authentication, wherein clients will use their password again to recover these credentials and then perform a mutually authenticated key exchange. And there's a number of different authenticated key exchanges you could use. Number of different credentials you could use, but this document takes a sort of opinionated stance and specifies a singular AKE based on 3DH with sufficient accommodations for future authenticated key exchange protocols if we want them later on. So perhaps something based on Sigma, based on HMQB. The delta between what's there currently for 3DH and what's needed for Sigma or HMQB or similar variants is quite small and really only varies in how the AKE specific piece does authentication with the public key credentials and how the key exchange transcript is computed. So the rest of opaque, sort of the core, remains the same and should be shared across all instantiations. Next slide, please. So between the last meeting and now, there have been a number of updates to the draft, some major and some minor. Major pieces that the whole thing was sort of massively refactored based on feedback from Eric Crockett at AWS and Amazon to sort of make it clear what is sort of the offline phase and what is sort of the online phase, and what's essentially to be done for the online phase. That is both sort of the credential recovery step as well as the authenticated key exchange step. So hopefully it's much more clear now. We also previously had sort of an odd balance in terms of things that were parameterized and things that were pinned in or baked into the document. So we had this hard dependency on HKDF and HMAC and so on. So to accommodate particular implementations that may want to use different MACs, so maybe CVC MAC or something like that, we've now abstracted over all of the underlying primitives such that anyone can plug in things that conform to these various interfaces, and the protocol should work and be safe to use. We've also done a lot to sort of prune and fix the wire format of the protocol so that implementations have a less difficult time parsing things, serializing things, and so on. With the exception of, I think, two fields off the top of my head, that is the identifiers that are used for client and server, and arbitrary application info that's exchanged during the authenticated key exchange step. Everything else is a fixed size and easily parsable. So that should help. Some minor things as well. Previously, the transcript for 3DH was minimal in terms of what it actually included for security. This was sort of an implementation headache in that it was there were sort of two different transcripts, one for actually key derivation, then another for computing the MAC and the actual key exchange for key confirmation. So we did as TLS does and just folded everything that was sent over the wire into the transcript to simplify the implementation and sort of the specification as well. We also added a suggested password file serialization format. The password file is the thing that the server stores that has like the users or the client's credentials in it. And the purpose of this is that opaque can be sort of treated as the black box on the server side that outputs password files that are then written to disk as just bytes, blobs of bytes, and then read from disk and potentially put back into the relevant APIs to be parsed. But servers and implementations are, of course, free to, store these things, serialize them however they want. But there's just a recommendation in there. And finally, we added test vectors, which goes nicely into the next slide. These test vectors are, we use them to interop with several different implementations. There's a reference implementation in Sage based on the underlying reference implementations in Sage for the OPRF as well as hash to curve. And that has achieved interop with OPKE, with the Ristretto, and with, I believe, Ristretto P256, and maybe another curve and a separate Go implementation. And I'm aware of others that are on the way as well. Haven't yet achieved interop, but are quickly approaching. So things are looking good on the implementation front. Next slide. Right, so there are basically two big-ish open issues right now, and I think we have clarity in terms of what we want to do for both of them. So I'll talk about both of them now. The first of which is how we actually store private keys. So currently in the document, the credentials as they're stored on the server always encrypt a private key that the client provides to the protocol. This is interesting because if you're a user interacting with the server and you know the username to use, the password to use, you can interact with the server, get the credentials, and recover the private key. And in doing that, what you have to do is like compute an OPRF or run an OPRF protocol with the server, and that OPRF output is like used to like derive a key that's then used to later decrypt the credentials. Basically, if you know the right inputs, you can compute this OPRF output and decrypt your private key and then use that to authenticate. So the observation was made that rather than storing any like encrypted version of a key on the server at all, why not just use the output of the OPRF, which protects the key as it's stored, to derive a key sort of inline, so to deterministically derive a key. And that would allow applications without any sort of external key generation function to just use opaque out of the box, derive keys and have one less input. So the proposal here is to sort of shuffle things around slightly such that there's effectively two high-level modes. One, which we're calling an internal mode, wherein keys are deterministically derived based on the output of the OPRF protocol. And then another, which is an external mode, wherein keys or applications that have keys that exist externally to opaque can import them and save them in the credential file, and then recover them later on. And this should accommodate things that are, I guess, both types of applications. And potentially, if there's weird AKEs in the future that don't have, nice deterministic key generation functions, they can just use the external mode. Richard?
Just a quick clarifying question on this external mode. This seems like this complicates the API, complicates the architecture a bit. Is there a reason that someone's interested in using external keys here? Because otherwise it seems like unnecessary complication to have another interface here.
So the primary motivation was trying to keep this future-proof, and in terms of like what, potentially there might be AKEs in the future wherein the actual deterministic key derivation function is not specified. I agree that it is a bit more complicated, and no, we don't currently have a use case in mind specifically for 3DH right now. We know how to deterministically derive keys for these groups, and we could get away with just using internal mode. But external mode is there specifically and solely for future use cases wherein that sort of derivation is not clear. I realize that may not be an answer everyone likes, but that's the rationale.
Yeah, I mean that seems fair enough. It also seems like you could add this flexibility point in the future version. But
we discussed. Yeah, the details are subtle enough in terms of like how you actually protect the envelope, because you need certain requirements for how you encrypt the envelope. Like you need like a key committing AED effectively. We kind of work around that in slightly in a certain way. And actually, we could talk on that later. So we felt it was appropriate to deal with it now, and rather than sort of delegate it to future specifications that might be tempted to potentially do that encryption incorrectly. But yeah, thanks.
Makes sense. Thanks.
Next slide, please. The second issue is sort of threat model specific. So currently, in the current version of the protocol, it's possible for an active attacker who's interacting with the server to sort of actively query, certain username password guesses and learn whether or not a user exists or does not exist, and then also learn if a user does exist if the password is correct or not correct. And if you compare this to other, authentication systems wherein it's possible for the server to reply indistinguishably, the user doesn't exist or the password is wrong. This is somewhat of a regression, and there's two things we can do to sort of mitigate this. The first of which is to specify sort of optional server-side behavior, wherein if a user doesn't exist, the server generates, quote, a fake response, a deterministic response, but it's fake. And this means that, like, if an adversary, given a snapshot of all the users in time, queries the server and the user doesn't exist, it will get back an answer. If it does exist, it will get back a different answer. It just won't know if the password was right or wrong. The problem with this is that, and later on, if this user is added to the system, or if the user that does exist password, if like credentials change under the hood or something, the server's response changes and the adversary can learn some information. So the second option is to be a bit, is to sort of augment the protocol slightly to make this sort of non-optional, wherein the server effectively encrypts its entire response to the client. And what this allows the server to do is, in the case of a non-existent user, just generate random bytes or random garbage. So from the attacker's perspective, they effectively learn no useful information as to whether or not the username exists, the password was right or wrong, and so on. And we seem to have found a fairly, a minimally invasive way to do the second option, which requires sort of minimal storage on the server, and we think is pretty reasonable to implement. The details are in the linked issue if you want to check it out. But currently we're leaning towards going towards that, and there's a pull request up for review. But if folks have opinions on either of the I guess the applicability of either of these attacks, we'd be interested to hear them. Next slide, please. So after we resolve these two issues, we should be ready to go. We expect to update all the implementations as well as the test vectors accordingly, and then hopefully ask for research group last call. That's it.
Thanks a lot, Chris. Any questions? One question from my side regarding the client enumeration issue. Could you please get back one slide to the issue number 24? Yes, thank you. Sorry, 22, yes. About the, no, the next slide, yes, thank you. So about the second option, Chris, could you please tell us more about the second option regarding the changes in the protocol? Don't these changes have any influence on the security proofs, on security assessments, etc., or are there are quite technical changes that do not affect security proof at all?
Yeah, the changes don't affect the security proofs. Hugo has confirmed that. This is more of, I guess, an application layer attack sort of thing. Yeah, I think it's I don't know how much detail you want about the particular change. Simply say that things are unaffected.
Your word is enough. So if you say that you feel that as an effect, that's enough for now.
I'm just relaying Hugo's word as well.
Okay, thank you. Any other questions? Then thanks a lot to Chris. That's a great work with OPEC. I believe that draft is really nearly ready to be ready for the group last call. Then let's go to the VLPRF discussion, please, Armando.
Yeah, please present. All right, my name is Armando Faz. I'm going to present about BOPRF's draft. Okay, next slide, please. Yeah, well, this is basically one slide refresher about the protocol. So this is a two-party client-server protocol. So the client knows some input X, the server holds a private key K, and they interact in order to compute a pseudo-random function that outputs this information Y that is only known by the client. But in this sense, the protocol is oblivious because the client only learns the output without learning anything about the server key. And at the same time, the server doesn't learn anything about the client's input and output too. Another mode is the verifiability mode in this construction, in which the server also gives a proof to the client that that the output was computed actually using the key K. And the player has the ability to verify that that the proof is correct. Okay, next slide. Right, so this is our list of the latest changes that was done in the current version. So the first two are based from removing one of the input, which is trying to enforce the domain separation as part of the input. So we give recommendation for that. Issue 239 is some updates on the proof generation. Basically, it's just updating the interface in order to be usable, in order to have a clear interface of the discrete logarithm proof. The last issue there is about using shake function for the decaf group. So this happened because it's likely that implementation for Cure 448 are likely accompanied by shake. So it makes sense to change from SHA to shake. Next slide, please. Yeah, so there are some current issues that we're discussing right now. This is one proposal. One new proposal is trying to put a verifier mode which doesn't use zero knowledge proofs at all. So this construction was published in this sprint, 2020-72. Yeah, basically no proof is transmitted and only presents changes on the client side. Server still computes this scalar multiplication k times t0, and basically on the left is what is in the current mode, and on the right is the new proposal. Basically, it adds some point that can be one additional point that can be used as a mask. And this can be cleaned using the public key of the server. So in order to verify a set of tokens or a set of because there is no proof in this case, so the client needs to do a linear combination of tokens and then do an issuance operation. So this is one way that the client can verify tokens without using an explicit proof. Next slide, please. There's another a very recent issue or warning, let's say, about how to do blinding. So okay, so here just to set some notation. So we work in a group in multiplicative notation. So basically, the main result of the paper or that is pointing is that exponential blinding is safe, but there are some use cases in which the multiplicative blinding could be unsafe. So there is one proposal to do in how we can do depart from this is on issue 241 and yeah. So next slide, please, which is my final slide. Just to hear the questions and also in response to the CPACE talk. So yeah, we can coordinate about the implementation efforts. Thank you.
Great. Thanks a lot, Armando. Questions, comments? We'll get back to some issues regarding the VOPRFs because we have our last presentation for today in an hour from Sabot about VOPRF with public metadata. So some questions may raise during that presentation. Do you have any questions now? Going once, going twice. Okay, thanks a lot, Armando. Then our next item, RSA blind signatures. Chris Wood.
Yep. All right. Are we good?
Yes.
Great. Yeah. So this is a proposal for bringing something that people use quite widely and have been using for a long time to Cfrg to see if there's interest in standardizing this quite useful tool. So next slide, please. So motivation, Armando just gave a talk on VOPRFs, but I'll summarize sort of the high-level functionality here. VOPRF is effectively a multi-party protocol for computing this PRFF, given a server secret key K and client input X, and in such a way that the server learns nothing of the client's input X and the client only learns the output Y. Pretty simple. Next slide, please. This tremendously simple functionality has found its way into a number of different applications, Privacy Fast perhaps being the first one at a larger scale. But there's also been sort of a number of alternative applications that require a similar functionality, but with sort of different constraints. So Tor has come up with a proposal for applying something that has the shape of a VOPRF for denial of service prevention to sort of help check that things connecting to relays are authenticated and attested at some point. There's also been a proposal for using something like VOPRFs for click fraud prevention up in the W3C space. And VOPRFs don't quite work for some of these cases, primarily because in order for them to be useful, it requires either widely shared secrets, because only the owner of the private key can actually verify that the PRF was actually computed correctly, or you centralize access to this key and induce heavy load on the thing that actually is performing VOPRF evaluations. And if this is like an HSM or something like that, you potentially you run into potential scaling issues. Next slide, please. So blind signatures can help here. Blind signatures are functionally quite similar to VOPRFs, with the distinction that the outputs are publicly verifiable, which is quite nice. That means anyone who has a message, an input message and a signature pair can verify it. So you don't have to share secret keys quite widely. You can have other entities in the system verify the signatures that are not the signer. And that seems like it would at least check two of the applications on the previous slide off. And there are a number of blind signature schemes that exist in practice. So we have blind Schnorr signatures, small asterisks because some of those are not such great shape right now. Blind BLS based on pairings, Abe paper, and then of course Sean blind RSA. And there are others as well, I'm sure, that I've not included here. Don't mean for this list to be exhaustive. Next slide, please. And there's a lot of, in looking at the landscape, there are a lot of trade-offs and considerations that we might take into account. So for example, for BLS, which is really quite elegant, it's very easy to specify, very easy, I guess, to reason about, but based on pairings being perhaps not as widely distributed or as widely used as we would like they're not in most major libraries like Boring SSL, Ring, etc. That's sort of a barrier to adoption. They also have more expensive signing and verification costs. Schnorr is also really nice, super lightweight, threshold friendly. See Frost and Chelsea's going to talk about that later. It does have the downside in that it requires 3 messages. First, the server commits to a nonce, and then the actual client server engage in the signature computation. And working around that perhaps requires state on the server side or additional computation overhead. But perhaps more importantly, there's this pretty great paper from folks at Google and elsewhere where they effectively broke a number of variants of blind Schnorr signature schemes. And I think it's at Eurocrypt actually this year where it was accepted. But all that is to say, like this gives us pause about blind Schnorr right now. There is though a very promising sort of patch that was published last year that does seem plausible and a way forward. But given the state of affairs, it gives us sort of concern. And then we have, I guess, RSA. RSA is, of course, widely supported for obvious reasons. Does have the downside that it's large signature sizes, larger than elliptic curves. It is not easy to threshold. It's RSA. There's sort of several cons, but one of the very nice, some of the very nice properties about it are that it does run in a single round, so completely stateless issuance on the server side. So I can run the protocol without any additional state, and I can scale as needed effectively. But importantly, in considering the impact of the ecosystem and adopting something like blind RSA signatures, support for verification is already widely supported. So really only the sort of generation side needs to change, which is a compelling property. Next slide, please. So the protocol basically works as follows. The client gets out of band the server's public key, SKS in this particular case, and with this particular public key in a message, feeds it into this blind function to produce some blinded output, shoots that over to the server, who then signs it with its private key and sends that back to the client, who removes the blind and produces the signature and can verify the signature in real time and drop it if it's invalid or not. Quite simple, and this is like a one-to-one mapping effectively with the OPRF and VOPRF API, especially the VOPRF API, because the client needs the knowledge of the server's public key in order to actually verify things. So this should sort of be a drop-in kind of replacement for applications that are already built on VOPRFs that require this additional public verifiability step. Next slide, please. Of course, being RSA, there are a number of potential pitfalls. Perhaps most importantly is or perhaps first on everyone's top on everyone's mind is what encoding function do we use? And there are a number of variants, be it PSS, full domain hash, or PKCS. And in looking at the different options and looking at the sort of the literature, it seems safest it seems safe to go with either PSS or full domain hash. And the determination between which of those two we went with was largely dependent on availability of existing libraries, especially in the verification path, wherein PSS signature verification code is already, it's definitely in most of the major TLS stack libraries by virtue of TLS. And it also supports randomized and deterministic signature usage the application wanted by changing what the salt is. Of course, like this is, we could probably go either way here. We don't feel super strongly about PSS versus FDH. And there was a lively discussion on the mailing list about which of these encoding functions is best. And so I'd be curious to hear what people think about that. Next slide, please. So the current status, we have several interoperable implementations with test vectors in the draft. It's a very simple thing to implement. Many people have done it, and we think the spec as written is quite stable. And given that it solves this specific charter item in the privacy pass working group, and that is the ability to instantiate or to invoke privacy pass and produce tokens that are publicly verifiable. We think there's perhaps wider interest outside of Cfrg for this particular construction. Next slide, please. So the two questions for the group are, I guess, first and foremost, is there interest in working on blind signatures? Given sort of the activity on the list, the answer would appear to be yes. And the second question is, assuming yes, is there interest in adopting this document as a starting point? And with that, I will I'll pause for questions.
Thanks a lot, Chris. So, do I understand correctly that you would like to ask the group whether there is interest in adopting the document and on any other ways of working on the topic itself, right?
Yes.
One small question from my side.
Well, I can provide them if there are questions about the dog as well. I can provide them if they're actually deciding.
Please.
Christy?
I couldn't hear over the dog, it's very cute. So, you said that this solves the Privacy Pass charter item to support public verifiability. So just wondered,
yes.
Have you had presumably discussions with the Privacy Pass group about this? Like, do you know that this is a solution they would want to pursue? Has it had any airing there? Just kind of a question on like, is this like one solution among many they're considering, or do they not have a solution currently? Thanks.
Yeah, blind RSA, there was a thread on public verifiability in the Privacy Pass mailing list. There was no clear sort of consensus in terms of which construction was, I guess, actually desired, but I see Ben's in the queue, so maybe he has a better, being the chair, perhaps he's a better answer.
Hi, Ben Schwartz, Privacy Pass chair. So, yeah, I was just going to say the same thing. There was a discussion on the question of using a scheme in the context of Privacy Pass. I would characterize that as positive interest in that possibility from the working group. RSA specifically wasn't mentioned. That thread was focused on the BLS algorithm, but I think the working group, at least overall, is interested in at least looking at blind signatures and having a concrete format to talk about them.
Yeah, I guess that kind of answers my question in as much as like there's interest in looking at blind signatures, but not like agreement on blind RSA as the way forward. Did I understand that right?
Tommy?
So in the Privacy Pass charter, there is, I think it's, I'd have to go look at the text again, but I believe it's fairly clear that the charter is not meant to select a single algorithm. It's intended to have some degree of crypto agility. So I think I think that Privacy Pass is I think not really likely to formally exclude any particular suitable algorithm.
Yeah, just to follow up on that, in working on the protocol, the Privacy Pass protocol spec, we're trying to make sort of high-level accommodations for any underlying cryptographic primitive that has different properties in terms of like what sort of public metadata it supports, whether or not it's publicly verifiable or not, and we'll talk about those in the session later today. But this seems very much like something, a situation where in Cfrg we present a candidate, and then provided that it's suitable, Privacy Pass would just wrap around it.
Tommy?
Hello, this is Tommy Polley from Apple. So, I mean, blind signatures is definitely something that we're interested in, and I have a strong interest in having, you know, at least one good solution in this area. To the overall point of adoption use on this, I want to highlight a comment from the chat from John Matson, and I think the key point here is that yes, you know, it looks like doing blind signatures is important, and I want to highlight, like, if we do this, we don't want to rule out other types of blind signatures. I view this as, for all the reasons that Chris pointed out, a very easy one to specify that could get testing and deployment, and we don't think has obvious problems with security or attacks, but it would be essentially the first flavor of it. So for people who want to do early blind signatures that are publicly verifiable for Privacy Pass or other applications, we could specify it, use it, ship it, but then probably also expect to specify other blind signature algorithms in the future that people would shift to. But having this in the suite, in the arsenal of things we can use, I believe would be a very positive step.
Yeah, just want to also follow up on that. I mean, this is being used, like a variant of blind RSA is being used in production for a number of products. Like the Google VPN that came out recently uses this, and yeah, it seems safe. People are comfortable with RSA enough right now. Definitely don't want to like rule out future improvements, but this seems like something that we could do now and would solve pretty real use cases. So, Ben?
So, Nohat, the VOPRF drafts here specify an abstract VOPRF API. I think there's obviously been tremendous success with the same approach with HPKE, specifying a generalized set of requirements and an API for talking about them. What do you see the final state for that with blind signatures? Do we just reuse the VOPRF API? Do we need to adjust the VOPRF draft to specify that this API covers both basic VOPRFs and blind signature schemes?
So it's a good question. The intent was to make the shape of this API very similar to that of the VOPRF, but I'm hesitant to try to fold it in, specifically because the sort of semantics of the two constructions are different with this public verifiability difference. Ideally, or at least ideally to me, the difference would be sort of at the layer above that calls into one of these APIs. So like we might accommodate like the public verifiability aspect, or whether or not there's public metadata or not in the computation at the privacy pass level, and not in this particular, not in the VOPRF doc, and not specifically in the blind RSA doc.
Okay. So just as a sort of layering question for privacy pass, I think it would be great to have a clear abstraction boundary that we're supposed to use, because privacy pass probably shouldn't be directly referencing blind RSA per se.
Yeah, we're gonna have to. Like, part of the problem with privacy pass is that we haven't yet gone through the exercise of sort of composing it with different underlying cryptographic constructions yet. But now that we have like one candidate in blind RSA signatures, and there's also like the PMB token as well, and then like Facebook's private stats protocol as well. We now have like the opportunity to figure out what the API boundaries are. So right now it seems like nothing will change in these particular documents, but maybe it will, depending on how that exercise goes. But thanks for pointing that out.
So we'll cut the queue after Frederick.
So I'd like to cut the queue after Frederick. So please, Watson.
Watson Ladd, Cloudflare. There is a difference between the semantics of a blind signature and OPRF. We can talk about this on a list, but I don't think they should have the same API because they provide different properties. It's going to be very similar, but they're subtly different.
I guess I mean, one of Ben's like potential points is that you could instantiate or simulate an OPRF with a blind signature. In fact, one of the DirectKey's early results basically demonstrate that you can do so safely. But I agree, like the semantics are different enough at a lower level that perhaps folding them into the same API is not best. Fred?
I just wanted to make a note about the fact that we don't want to generalize the construction too quickly either, especially because some of the alternatives and other papers require multiple step issuance, or there might be some semantic differences there. So maybe we can see a bit like what other alternatives there are to RSA. And once we have confidence that we could come up with the right abstraction for it, then we could move towards adopting that. But if in the short term we're going to be using RSA, I think that building an abstraction on top of it, if it's not clear that future scheme might be providing the same abstraction, doesn't seem wise.
So yeah, everyone should come to the privacy pass session later today where we'll talk about these API things.
Thanks a lot. I hope that we can take it to the list. I think that there is quite a fruitful discussion, and I think it should continue. So we'll send a message to the list about the possible working on this item. Thanks a lot. Please, Chelsea, threshold signatures.
Sure thing. I actually have a lot of slide transitions, so I don't know if it's easier for me to share directly. Okay. Let me see if I can do that. Okay, how is this?
We hope to see them soon.
Oh, sorry.
We don't see them now. Maybe you should select them all.
Yep, sorry. Let me try one more time. Okay.
Yes, we see slides.
Okay, great. Okay, hi, I'm Chelsea, and I'm giving the update on our draft of FROST, and FROST stands for Flexible Round Optimized Schnorr Threshold Signatures. So just a quick summary about what FROST is, in case you're not familiar with it. It's a 2-round Schnorr threshold signing protocol, or it can be optimized to a single round with pre-processing. And one thing that's kind of interesting about FROST is that it specifically trades off robustness for round efficiency. Signing operations in FROST are secure even when they're performed concurrently, so this improves upon prior work in literature against an adversary that controls up to T-1 signers. And in FROST, key generation can be performed either by a trusted dealer, just by straight Shamir secret sharing, or by a distributed key generation or a DKG protocol. So that's kind of in a nutshell what FROST is. So the current status, so it was adopted as a working group item at the end of January, so relatively soon. So with that, we're working on the first draft, and we're focusing on the implementation details that are not specified in the paper. So really, we're going through right now and just kind of fleshing out V1 and talking to people who've implemented FROST and trying to like flesh out those details. Another thing sort of externally to this effort is we're writing a second proof of security using standard assumptions. So something that came out of FROST and some similar protocols like MUSIG and a few others is that the approaches to proving these kind of quite complicated schemes like multi-signatures is not quite standard. So we're working on a way to standardize these proofs of security. And something that's exciting is there's actually several parallel implementations of FROST in both Rust and Go. So I recently was notified of one that was put out by JP Almason's group. So there's definitely a lot of independent interest in FROST, and people are implementing it right now. So I think that's a really positive sign. I'm going to summarize some of the feedback that we got from the call for adoption. So the paper for FROST sort of assumed a prime order curve. The feedback that we got in the call for adoption is that there was desire for EDDSA compatibility, so over curves like 25519 and 448. One thing I want to point out is that compatibility in this case will be for verification of signatures specifically. So, and this isn't super widely known, but using EDDSA style deterministic nonces is actually insecure in a multi-signer setting. So we've had questions like, is it possible to do deterministic FROST? And it's not. So our draft will specify signatures that are compatible with verification in, I think it's RFC 8032 that specifies these signature formats. Another piece of feedback we got was that pre-processing might be difficult to perform securely. So that first round might be tricky because it's super important that nonces are only used once. So this is something we're thinking about, and as I'll talk later, we're planning just to specify the 2-round scheme in our draft. Another thing we got is that it would be nice to sort of have the option to either use the trusted dealer, keygen, or the DKG. So the next steps for us, so we'll be fleshing out our V1, so expect to see a full draft soon. We do need to start testing interoperability between implementations. And then, as I said before, we do need to adapt the draft to curves with cofactors. So we've looked at this just sort of in very briefly, but things we need to do is specify point validation during signing as required by these curves, and making sure that our signatures are verification compatible. So expect to see that in our next update. So our roadmap for the draft, within the core draft, like I said, we'll be specifying with a trusted dealer. I think that's kind of the easiest key generation option, and I think sort of commonly desired. We'll just be doing the 2-round scheme for simplicity. And we do have the concept of a signature aggregator, so we'll be specifying them as a non-signing party. So they could be a signing party if they want to, but we'll be keeping these concepts separate. One thing I wanted to mention that for just general interest within the working group as possible future extensions beyond Frost. One thing is that of pre-processing. So as I said, single round signing is possible in Frost, but there can be some sharp edges because it's important that nonces are used once. So I think this is something that's worth considering after we do this work. Another thing is specifying this DKG. So this DKG could possibly be more generally useful beyond just Frost. And so we wanted to put this out there as something that, you know, the working group or the research group might be interested in, but kind of more general. And then finally, something that's forgotten about all the time, but that's really extremely useful for threshold signatures or just threshold schemes in general, is that of share recovery or the ability to add new participants. So these algorithms exist. They're well known. They've been around for a long time. So I think maybe considering this as an extension might be helpful for failure recovery in practice. And with that, I'll take questions.
Please, Peter.
Yeah, you said you're focusing on the dealer version. I'd like to encourage you to also consider the case where you have a crypto coprocessor built into the CPU, and you want an application program to be able to securely delegate a partial threshold operation of a signature to the CPU so that then we can bind the operations to the CPU. And the reason for that is that I believe that there's going to be a requirement out there fairly soon for that type of processor. And signature is going to be one of 3 functions that is going to be really important to get presented as a package.
Okay, so are you advocating for the DKG then, so that these are 2, I mean, the key generation is distributed, or?
Yes, the key generation will be distributed, but doesn't need to be distributed using Shamir and whatever. It's just a question of being able to bind a signature key to a particular device so that you know that if the device is lost, the ability to create that signature is also lost. You can't extract, you can't take a backup and then use that to create signatures unless you've also got the device.
Okay, I think that's a specific use case, so I'm happy to have another discussion, more detail about that. So.
Yes, the use case, not the implementation that I care about.
Please, Richard.
Hi, thanks for the presentation, Chelsea. Just wanted to pick up on this point about the DKG here. Jokes about Daniel Kahn-Gilmore aside, it's an interesting point that the DKG here is pretty separable. Your suggestion here is that might be useful to use other places. What I wonder is whether we might be able to simplify this draft by not including the DKG, or if you think that the DKG is, kind of structurally intertwined with the signing algorithm and worth keeping for that reason.
No, it's definitely not intertwined. And actually, yeah, I completely agree. So within the core draft, I think we should just specify the trusted dealer, and then say also if you want to do something more exotic like a DKG, here's what we expect for all the participants at the end of keygen. That's pretty simple. So yeah, I do think the DKG probably belongs in its own realm, and because there's a lot of things you can use it for, and as long as we get keys for all the participants that fulfill certain properties, then I think it's fine for it to be external.
Yeah, cool. I think that could simplify the draft a fair bit.
Thanks a lot. we're behind the schedule, so thanks a lot, Chelsea. Let's go to the next item. That's key committing EADs. Please, Julia. Nick, could you please share Julia's slides? Thanks a lot, Nick. Julia, please start.
Okay, thanks. So today I'll be laying out how real-world vulnerabilities have arisen because of non-committing AAD schemes, as well as discussing the current key committing AAD landscape and how we can hopefully head towards a standard. So next slide, please. So here I'll broadly discuss authenticated encryption, and to keep things simple, I'll ignore nonces and associated data in this presentation. So here in the setting, we have a client and a server, and they both share a secret key. The client chooses a plaintext message and encrypts it using its secret key to produce a ciphertext. Next slide, please. And the client sends the ciphertext over to the server, who can then decrypt to recover the plaintext using its own secret key. And of course, we expect that an attacker who sees the ciphertext won't be able to recover the plaintext without having access to the secret key. Next slide, please. And there are many popular AAD schemes out there, such as AES-GCM and XL-20 Poly 1305, among others. And they're popular for good reason. They are efficient, they're standardized, and they're widely supported by many libraries. They also guarantee many security properties, such as confidentiality and integrity, and they've been proven Trojan ciphertext attack secure. But there's one security property that they don't target, which is, next slide, please. Thanks. It's robustness, or also called committing AAD. Next slide, please. So in a non-committing AAD scheme, you can produce a ciphertext such that it can decrypt under two different keys. So next slide, please. So this becomes an issue in what we call partitioning oracle attacks. So this is a new class of attacks that I've worked on with my co-authors, Paul Grubbs and Tom Ristenpart, and this will appear at ESNIC Security this year. In this attack, you can create a ciphertext that decrypts under multiple keys, not just two, and its goal is to perform efficient password or key recovery. So here now in the setting, an attacker wants to learn the key stored by server, and the attacker has access to a set of possible keys and wants to learn which one the server is using. So the attacker can create a ciphertext such that it decrypts under half the keys. The attacker then queries, next slide, please. The attacker queries the key, the ciphertext to the server, and the server tries to decrypt using its own key. So next slide, please. And here the server was able to successfully decrypt because its key was in the set. So now the attacker learns that it can eliminate half of the keys in its key set, thereby reducing. So next slide, please. So notice that this means that the attacker can learn one bit of information about the key because of this non-committing AAD scheme that's used here. Next slide, please. So we found that these attacks were practical and looked at a few schemes in depth, including Shutterstock's proxy servers, as well as early implementations of Opaque. And we found that there were vulnerabilities or possible partitioning oracles elsewhere, including in HPKE, as well as AG file encryption tool, among others. And there have been other vulnerabilities stemming from non-committing AAD as well, including in Facebook Messenger's content moderation message ranking scheme, as well as a few services by Google and Amazon, which were found by researchers at Google and Amazon last year. So really, this all shows that there's a growing body of evidence that non-committing AAD can lead to vulnerabilities. Next slide, please. So then the natural question is, what do we use for a key committing AAD scheme? Next slide, please. And this is a bit hard to answer currently because there's no scheme standardized. Next slide, please. But there have been a few schemes suggested. This includes the zeros block check scheme, which modifies an AAD scheme to check that a block of recovered plain text is an all-zero string. So this has currently been adopted by libsodium, but it does incur an extra overhead by adding 64 bytes to each ciphertext. There's also the hash key check, which modifies an AAD scheme to check a SHA-256 hash of the key during decryption. This has been adopted by the AWS encryption SDK, but again, it incurs this extra overhead over the base scheme by adding 32 bytes. Another scheme suggested is the single key encrypt in HMAC, which doesn't have any extra overhead because it is the base scheme, but potentially could be less efficient than these alternatives. And while the implementations, to our knowledge, don't have any sort of side channel, it could be that the zeros block check and hash key check could have some side channels if they're implemented incorrectly, and the zeros block check would also need to be implemented and analyzed separately for each AAD scheme. So each of these schemes sort of has their own pros and cons. Next slide, please. So currently there's some questions in this space. So Chris Wood, Paul Grubbs, Tom Ristipart, and I are planning to start a draft for key committing AAD. So we would love to hear your thoughts about needs and requirements surrounding this. So thank you very much, and I'm happy to take any questions.
One thing correctly is that if we move to the discussion of adoption of this as a work item, we will do this as some work of some framework of making of key committing AAD mode from any strong and secure AAD, right? So we don't want to specify some specific key committing AAD modes with some, for example, with some Chacha or something. So just some framework that can help to build key committing AAD from any secure AAD, right?
Yeah, we could suggest that, but there's also, for instance, like encrypt and HMAC as a standalone AAD scheme would work. We could also, in the draft, specify these sorts of transforms and be specific about the trade-offs with these multiple schemes. But that's one way to go.
Thanks. Please, Richard.
Yeah, just on the question of what schemes to standardize here, I think that might be plausible to take a kind of short-term and long-term view here. I think the just encrypt plus HMAC is probably the easy, quick win here because there's already a fair bit of prior art and deployment out there that would benefit from standardization and security analysis to make sure that the construction is put together the right way. There's like a few different ways that people put together encrypt and HMAC to come up with what they believe to be an AAD, which is not in all cases. So like having a standardized construction for that, I think would be useful and fairly straightforward to put together. But I think it could also be useful to to explore some of the other design space here. I'm obviously less familiar with what the opportunities there are, but I think that we could do two things here and it wouldn't be too crazy.
Yeah, that's a great suggestion. Yeah, I would love to see a single key encrypt and HMAC standard. There aren't any to my knowledge, so having that as a source for people to refer to for committing AAD would be great.
I have sketched one in the work we're doing in the S-Frame working group. I will post a link in the chat. I would love to get that analyzed and vetted by someone who is better at this than I am.
Yeah, that'd be great. Thanks.
Thanks. We'll have to cut the queue after Benjamin because we already have the schedule. Martin, please.
So thanks for going through this. This is the question I had was pretty simple. The two options you had with zero pad and I forget the other one had fixed overheads. Yeah, the hash key check. They had a fixed overhead, and it seems to me obvious that the hash key check, the strength of that is based on the strength of the number of bytes that you provide. Is there a version of this can you put 32 bytes in the ciphertext in the 0 block check and get a similar result, or is this you have to have a full block of some thing? Because that's 64 bytes is 4 blocks of AES, for instance. Don't quite understand how that's working.
So the reason it's 64 bytes is because libsodium is using, I think, xchacha 20.1305, and their single block of ciphertext is 64 bytes. So they just made an all-zero string for 64 bytes, but you certainly don't need that many bytes. But so that would be helpful to for standard to say how long of a zero string you would actually need.
Right, that was my intuition as well. So thanks for confirming that.
Benjamin, please.
So my understanding is that this is an attack against low entropy key spaces. Is that correct?
Yes, yeah.
Okay. I think something that would be really valuable here from Cfrg is a formal recommendation about the minimum entropy of key space to use with AES-GCM or the existing AE80s.
Okay, yeah, that's a great suggestion. I'll take note of that.
Okay, we'll take it to the list. Thanks a lot, Julia. That was a great presentation. Thank you. And the last item for today, Sabot, VOPRF with public metadata. Are you ready? I'm not sure that Sabot is here.
I don't see Sabot in the list.
Chris, maybe you present because you're one of the authors. Huh?
Sure. Let me. Yes. Sure. Yes, I'm happy to do so if he's not here. Okay. Yeah. Sorry, paging everything in. So this is an extension that the Sabot and Anand put together, and along with their colleagues, for extending the existing VOPRF construction to accommodate public metadata into the output of the OPRF evaluation. The motivations for this are primarily privacy pass in this particular case, which has an issue, the issue referenced here, for accommodating metadata both on the client side as well as on the server side. You know, I guess the dimensions of the metadata are still like a topic of discussion in privacy pass. But generally, there is not yet a construction that exists for safely folding in this types of metadata. And there's lots of different types of metadata you might want to use. So, for example, you could, if you wanted to bound the sort of the scope. Oh, I'm sorry. Can you go back to the previous slide? You might want to bound the scope of the OPRF evaluation by including like an expiration timestamp or something as public metadata, or something else to constrain or to sort of augment the output. We'll note that there's like a naive way to do this, and that is to just say for each bit of metadata, have a unique public key. But that doesn't scale very well, and for privacy reasons, we don't want to have many keys floating around. So next slide, please. Right. So the basic idea is to, rather than just run the VOPRF with a sort of fixed public key, to derive the public key based on public metadata. So in this construction, there is a main public key and a main private key, and there is attributes that are represented as bit vectors, and the from each bit vector, you can derive a unique key pair that can then be used directly in the existing VOPRF construction without augmentation at all. If you advanced one slide, the key point here is that the derivation from root or main public key to an attribute or metadata specific key pair is verifiable using sort of the similar discrete log equality proofs that we have in the VO-PREF doc right now. Excuse me. Yeah, don't really want to say much more than that. Summary of its properties: it is not depending on any pairings, which is quite nice. See previous RSA talk about why blind BLS does not currently work for many applications. It's based on sort of well understood PRF constructions, and it folds very nicely extends the existing proof construction mechanisms in the VO-PRF document. All the key derivation stuff can actually happen offline. Depending on the size of the metadata, that could be quite advantageous, considering that the proofs needed for checking that a particular derivation is correct scale with the number of bits in metadata. So I like typical applications or expected applications might use anywhere from like 8 to 32 bits of metadata, which is reasonable to do offline and then cache on the server or on the client. Sorry. So all this is to say, you can handle metadata quite easily offline, and then run sort of the super efficient VO-PRF protocol online, and the output. The result of combining these two is you have now VO-PRF with public metadata folded in. Next slide, please. What did he want to say here? Not sure what, I mean, it doesn't make much sense, I guess, to go into the details. Yeah, I guess we can just talk about the comparison. As I was saying earlier, it's possible to do this sort of key-based metadata construction right now in a naive way. You can have a single bit of metadata for a particular key. However, that scales, as I said, quite poorly. For n bits, you have n public keys, and there's no proof that the key is actually correct. But this would be, of course, compatible with the VO-PRF draft, because you just have a pile of keys you use, and you pick which one depending on which value of your metadata you want. Compare this to something like Pythia, which is a pairing-based OPRF that does also include public metadata, has constant size public keys and compute overhead, but it is based on pairings, and as a result, different hardness assumptions and different availability and implementation difficulty. The attribute-based VO-PRF, which is the sort of the construction right here, has logarithmic public key size, and depending on I guess the number of bits in your metadata, that can be I guess good or bad. And as I said, all this can kind of happen offline. I mean, there was another recent result a couple weeks ago. I don't recall exactly when it came out. That has a different construction for folding in public metadata that does not derive it from the keys itself, but rather augments the OPRF evaluation key based on metadata, and then slightly changes how the discrete log or the VO-PRF proof is generated. This is great in that public key size is still constant. There's not like Lothberg for each attributes. But it does not fold easily into the VO-PRF draft currently, because it requires changes to the proof. It also requires changes to the OPRF, like the private key evaluation, in line with the protocol. and also there's no like API slot for folding in metadata right now. At the API level of actually doing the evaluation on the server side. Whereas with the proposal here, the metadata could be folded into the public key generation step and verification step that happens before the VOPR protocol is run, which is a nice alternative. It was also pointed out in the privacy pass list. Oh, sorry. It was also pointed out in the privacy pass list that one could use as an alternative to the single bit per metadata key solution. One could optimize that slightly by using Merkle trees. So, for example, you could have imagine you had like a list of keys where each key is a leaf in a tree, and imagine you built like a Merkle tree on top of that, and you gave clients the sign tree head, or effectively the tree head in this particular case, and then in running like the VOPRF protocol, what you give them as sort of proof of the key to use is the leaf public key itself, which is just like a single element, along with the path to the root, or the copath to the root, so they can verify that it was correctly included in the tree. But this is more just an optimization in terms of working around the huge pile of keys in the naive method, but maybe something worth documenting. Next slide, please. Yeah, so the question for the group is, first, is there interest in a VOPF variant with public metadata? There certainly seems to be a number of instances that I'm aware of where being able to fold in something something public that is cryptographically bound to the OPRF output would be really nice. So I hope the answer to this is yes. And I guess if so, what sort of, I guess, assumptions are we comfortable with relying on for supporting this? So, for example, the attribute-based VOPRF variant that is this particular presentation has a different hardness assumption from the more recent anonymous tokens draft or paper that was discussed in the privacy pass mailing list. Unclear what the difference is in hardness assumptions, what the sort of high-level impact is on the security of the scheme. And it's unclear which of these we're comfortable with standardizing now. Also, because this draft sort of extends the existing APIs and the shape and mechanics of the VOPRF draft without any modification, I guess we're just generally interested to know if this is something the research group would be interested in working on and adopting, either as a separate draft or folding into the existing draft. I think both seem pretty reasonable. So apologize for clobbering that together. I didn't expect to present.
Thanks a lot, Chris. That was a great presentation, despite the fact that you hadn't planned to do this. Thank you again. We have time only for one question, I think. Yes, Cfrg.
There's a note from Nick in that the term attribute-based might be super confusing. Totally agree. It's officially called the attribute-based OPRF in the paper, but it's really just an OPRF with public metadata. So yeah, we can fix the name. Fred?
Abstractions, would there be the possibility to abstract the key augmentation part mechanism outside of like any use case for VOPRFs? Because I think there's a potential application for this to build a partially blinded signature scheme from an EC-based blind signature scheme using the same mechanism.
I didn't catch like the first couple bits, but what I think I heard you say is, could we like generalize this particular like key derivation, verify key derivation mechanism, and perhaps use it in other contexts, like for signature schemes or whatnot? I believe the answer is yes, because the key derivation mechanism is not specific to the OPRF in any way. It's a way to deterministically and verifiably derive keys that can be used in OPRF protocols, but could also be used in like other EC-based things for blind signatures and whatnot. So yeah, I think it's general in that way, and that's actually a good point, and perhaps a reason why it might be best left out of the VOPRF draft right now.
Thanks a lot. Chris, could you please move these questions to the mailing list? We don't have any time to discuss them now, unfortunately.
Yes, absolutely.
Thanks a lot. Thanks a lot again to Chris. So 5 minutes for any other business. Any comments, questions? So we have 4 minutes more, so maybe any comments about the presentations we had today?
Yes. I have a question. Oh, Philip was in the queue before. Oh, go ahead.
Yes, Philip goes first. Philip, we don't.
You're not sharing your audio.
Philip, we don't hear you.
Yeah.
Yes.
You can hear me now?
Yes, yes, yes.
Yeah. Okay. I was just going to ask about the threshold encryption, and I put in a draft, and I was told there was going to be a thing on the list, and it never happened. And then I was promised it again, and it never happened. And it's been over a year now. It's not for lack of prodding the chairs of the working group. You know, when we went over the threshold stuff this time last year, we agreed that, you know, we would take it to the list and there'd be discussion there. And there was discussion, and there was never it was never put to the list whether the group should consider the threshold encryption draft.
I'm sure that there was a conclusion of all our discussions about all threshold stuff in the mailing list from Nick. Maybe Nick can comment on this.
Yeah, so we discussed threshold signatures as a topic, and we haven't gotten to threshold encryption. That's my understanding.
Right. Well, when are we going to get to it? I mean, you know, I've been waiting a year. You know, I gave a presentation a year ago.
Yeah. Does anybody else in the working group or the research group, have interest in this? I think this is something that we can bring to the list. I think the reluctance to do this immediately had to do with lack of enthusiasm beyond the requests from one person. So if other folks in this meeting have interest in this particular topic as something that CFRG should approach, I encourage you to step to the mic line.
And we have only 1 minute left, so maybe last comment from Chris.
Yeah, this was just I wanted to follow up on something Bjorn was discussing or proposed earlier in his CPACE presentation, specifically around like standard reference implementations for the VOPRF, hash to curve, and the PAKE protocols. Should we be doing something here? I guess sort of from the CFRG's perspective, like trying to collect standard reference implementations for each of these things that people can reference. For the drafts that I assist with, we've been using Sage because we want to make it very clear that this is something, this is code to be used to understand the protocol and the specification. Definitely not something you should ship. And I think Sage is annoying enough to make that very obvious. But there's a good argument to be made that perhaps there should be, standard C implementations for most of these things, or Rust, as is sort of common in these cryptographic competitions and whatnot. So I'm curious to know, A, if people are interested in this sort of thing, and B, how we might sort of collaborate and make it happen.
As potential document shepherd for CPACE draft, I am fully support your point. Could you please take it also to the list, because our time is out.
Absolutely.
Many thanks to everyone. So we have to finish now. Thank you, folks. Bye.